I'm on the surface. It's very much like Mars. Its size, internal structure and atmosphere resemble closely our red planet. With all the drones scanning this planet and monitoring its sun, hopefully we'll be finally able to find some clues about who broadcasted the signal.
Maurizio, we're picking up some activity close to your location.
What kind of activity?
Electromagnetic. Something's happening close to where you are. We're sending a drone to get more data. You better hurry back to the pod.
What are you talking about? There's nothing here. I can hear you, Dave. What's going on? What? What is? There was nothing here a minute ago. Dave, do you copy? This must be an hologram. Dave, can you see anything? Do you get my signal? Okay, I'm going to tap all of these. It must be the Institute. This was in the 21st century. He looks like frozen in time. Let's see where he's gone. Nobody's here. It's unbelievable. They must have got all of these from the memory banks of the spaceship. Another room here. Telescope control. The Liverpool telescope, actually. Yeah, that must be that. It was the larger robotic telescope at its time. Another simulation. Nobody.
Some more activity from the surface. Maurizio, do you copy?
I'm running back to the pod.
We lost both video and audio contact. What happened?
You will see the recording from my camera. It's extraordinary.
We've just picked up a signal originating from your last recorded location. It's a very narrow beam of energy. We're trying to establish its direction.
I've reached the pod. I'll take off in a few minutes.
We have tracked a radio signal generated from the surface of the planet orbiting Tau Bootie's companion star, and we have reached the wormhole. We are now beyond its exit point, near the center of the globular cluster Omega Centauri, in the halo of our galaxy. We are now 60,000 light-years from Earth. Globular clusters are very old systems of stars, kept together by their force of gravity. They orbit around the disk of our galaxy, in the halo. Globular clusters host between 100,000 and 1 million stars, strongly concentrated towards their centers. Omega Centauri is exceptionally massive, and its core is so crowded that the average distance between neighboring stars is just a tenth of a light year. In comparison, the star closest to the Sun is 4 light years away. Seen from a planet orbiting a star in the cluster core, the night sky will be immensely brighter than on Earth.
The stars that inhabit globular clusters are old, almost as old as the age of the universe. Indeed, the age of these stars has been used to constrain the age of the galaxy. In the late 20th and early 21st centuries, this was a field of research that John Moores University was at the forefront of.
The age of globular clusters can be estimated by studying their stars. Stars are giant gas spheres, and their evolution in time is a struggle for survival against gravity. The gas particles need to have energy and move around to avoid being crushed together by the star's gravity. The energy is usually provided by nuclear reactions, as in our Sun. Nuclear reactions are effective deep inside stars, where temperature and densities are much higher than at the surface. In the Sun, the central temperature is 16 million degrees Celsius, while at the surface it is of only 5,500 degrees. The chemical elements involved in these nuclear reactions depend on the age of the star. In general, over 90% of the life of a star is spent transforming hydrogen nuclei into helium nuclei in its core, during a phase called main sequence. All in the final stages of the evolution of stars up to about 6 times the mass of the Sun, nuclear reactions are not necessary for the star's survival, because the gas is so dense that even gravity cannot squeeze it. This is the white dwarf phase, when stars slowly cool down and get increasingly fainter because of the lack of nuclear reactions. More massive stars do not become white dwarfs, and eventually explode as supernovae, leaving behind a small remnant in the form of a neutron star or a black hole. Astrophysicists use the so-called color magnitude diagram of stars as a tool to investigate their age. This diagram displays the luminosity of a star against its color. Moving upwards in the diagram, stars become more luminous, whereas moving from the left to the right, the colors change from blue to red. This means that the star's surface temperatures become colder. Stars are not distributed at random in this diagram, but occupy well-defined sequences. They correspond to different stages of evolution. Stars change in time both luminosity and surface temperatures in a way that depends on their mass, age, and initial chemical composition.
A colour magnitude diagram is like the ID of a star cluster. Different star clusters have different CMDs. From the observed CMDs, we are able to derive several properties of the cluster stars, like their age and distance. There are several techniques we can use to study the CMD of stellar populations. These have been applied and described a long time ago by scientists at Liverpool John Moores University.
Globular cluster stars move in orbits, like the Sun orbits around the disk of the galaxy. They depend on the strength of gravity, that is, on how much mass is in the cluster. The measured velocity of the stars in the center of Omega Centauri are higher than expected from the number and type of stars seen. There has to be something very massive and invisible, a black hole of about 40,000 solar masses. A black hole is a region where space is so tightly warped by gravity that not even light can escape. Massive stars can produce black holes after their explosion as supernovae, but these stellar black holes can have at most a few solar masses. Many black holes close to each other can coalesce, forming a much more massive object. Also, they can accrete matter from their surroundings due to their strong gravitational field, and eventually grow in mass.